So today we're going to talk about my lithium iron phosphate 16 cell 48 volt battery. I built this from parts from China, and I put it all together with a JK BMS, and we're going to go through all the different cells, how to measure their voltage, how to put the battery together, how to configure the BMS, what kind of fuses you need, what kind of shutoff switches you need, so that you can build something the equivalent of this, which in this case is a 48 volt battery, or the equivalent of 15.6 kilowatt hours of energy storage in this battery. It is a DIY battery that costs a fraction of the cost of a typical lithium iron phosphate battery. So I will show you step by step where I got the cells, where I got the parts, and how I put it together. Stay tuned. We're getting started right now. So let's talk a little bit about the DIY battery and the compartment that I have here. And I don't know if you can see all of this yet. Let me see if I can zoom out far enough so you can see it. So this side is plywood, and this far side over here is plywood, and it holds the battery together. As you can see, I have these iron bars that go through. So let me get this set back up, and then I'm gonna pull this cover off so you can see the full battery, and we can walk through each of the steps in the process of setting it up, configuring it, and testing it, and all that kind of stuff. So as you can see, I have I don't know if you can see that yet. Let's see. There we go. So you can see here I have 16 cells, and they start over here as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All 16 cells are 3.65 maximum volts, and the minimum voltage on them, they are Eve cells, and basically the scan codes and everything you can see. If you're interested in looking those up, I'll include some close-up pictures of these for you. But these run in series, 16 in a series, for 51.2 volts or a 48 volt battery. It's a 16S battery. I got these, I ordered them off of, from China in November, December. And when they came in, I assembled this battery. I connected them to the I connected them to the JK BMS, and they go through a T-fuse, a shut-off switch on the positive side, and they go through a bus bar on the negative side, straight over to the battery, to the other battery bus bar. Now, I'm going to walk through a couple of different things that I did as I was setting this up. One of the first things I did was I tried to balance all of the cells. These days, as long as they start off pretty close, the 2 amp balancer that is in the JK BMS can pretty much get you home if you start off pretty close. Being it was my first battery, I did not take that to heart. I actually bought a battery charger and charged each of the cells and invalidated each one of them. So I'm going to show you kind of how that aspect of building a battery works so that you understand it. As you can see, it's got bus bars connecting the positive and negative here, and then here. I've also put some tape over top of these. This prevents me from accidentally getting something on them that causes a short. There is a lot of voltage in these batteries, and they can put out a lot of amperage, and even a simple wrench can short out on these and cause you really big time problems. As you can see, all the lead wires run down and over into the BMS, and all of them are wound up here nice and clean. The positives come off of the positive side, the negative comes off of the negative side here, and basically so the positive runs straight up into the battery bank, and the negative is the one that goes through the BMS and controls the input and all of that kind of stuff to it. Each one of these I can show you with a meter how we test them. and how we go through them. But no, the basic design is the cells on the negative side connect to the BMS. The BMS goes to a bus. The positive runs through a T-fuse, a shutoff switch, and then goes over to the bus over there. And I can even show you the bus bars over here so that you understand the negative coming out of the BMS. I ran it up into a bus bar because it had these two 7/0 wires on there, and I didn't want to try to get them, stretch them over here. So I ran them into this little bus bar here, and then from there I ran the regular 1/0 wire that I use for batteries over to the standard bus bar, and these run to the 3 EG4 batteries behind the scene. The positive bus bar, it runs out of the battery BMS into this T-fuse. After it goes to the T-fuse, it goes to a shutoff switch. This is a 60 volt rated shutoff switch from, be very careful. There's a lot of 48 volt ones out there, and they don't actually support Life Power 4 batteries because their voltage is standard over 48 volts. So be very careful. This is a Victron shutoff switch, which allows it to support up to 60 volts. And then from there, it runs over to the bus bar here, and this runs back to the EG3 batteries or EG4 batteries on the back also. So that's basically the DIY battery itself. And what I will do is I will grab us a meter, and we can go through testing a few of the cells, and I can kind of show you how to look at the cells and how to compare everything and check it out. So I'm going to try to change the angle a little bit here and give you a little bit better view of what's going on. So this is just a basic voltmeter that I got. It's a Klein Tools. You can use any of them. I like this one because it's fairly accurate and it's reasonably priced. But you're going to need one of these if you're going to be building batteries, any kind. So what I started off by doing is I'm going to see if I can put this someplace where you can actually see it. Maybe I can use my coffee cup. Great. I got that balanced on my coffee cup, believe it or not. So let me see if I can show you a couple of voltages. And so the idea here is that you want to test from the positive and the negative of each battery. And so you can do that by switching your voltmeter on and selecting DC power, as you can see here. And then once you've selected DC power, you can touch this to the positive and the negative terminals. So all of these wires here are connected to negative terminals. So this should tell you that if you want a negative terminal, you come to this side, and a positive terminal, you come to this side over here. Now I'm just going to peel back some of this tape a little bit so we can get to this battery and see this registers 3.319 volts. Now, a very well-balanced battery will have that same type of reading across multiple batteries. So I'm going to go to the next one here, and 3.319. And this bank, I have been very, very lucky since I got it. All of the batteries stay within a few milliamps of each other. And I will include an overlay here on the screen from my phone, which I'm actually using to record right now, of those all the different cells and everything. But you should be able to go to practically any cell in this series here and connect this and see the 3.17 there. And if I come over here again, I have 3.18. So within 1/100th of a milliamp of each other, or a millivolt of each other, which is very well balanced. So I went through each one of these, charged them all the way up to 3.65 volts, and then made sure that that when it got to that voltage, that it completely saturated the battery and that everything was there. And then when I connected them all up, you should be able to take the positive and the negative from the main terminals and see the whole voltage of the entire pack, 53.1 volts. Now, this also applies to anywhere within the pack. So we should be able to take the negative from this side, the positive from this side, and the negative from this side, and see half of the voltage pack, which is 26.55. Now, if we were configuring a 24-volt battery, there would be 8 cells in it. And if we were configuring a 12-volt battery, we would go here to 4 cells, and those 4 cells would be these 4 here, and you would be at 13.21. So as you can see, this is the same as taking 12-volt batteries and laying them in series, or two 24-volt batteries and laying them in series and creating a 48-volt battery. Now, when I installed these cells, I installed, as you saw from the original section of this video, I'm going to go a little bit more into detail now that we've done some voltage testing here. I'll move this out of the way, and I'm going to show you basically how I built the cabinet so that you understand what's needed to make this work. So I built 3 different sections of the cabinet here. And as you can see, I have 2 bars that are screw nuts that can allow me to tighten this. Now, it isn't real compression. What it is just lightly holding them with a light amount of pressure, holding them all in place and keeping them from expanding or shrinking or moving or whatnot. Now, some people talk about compression and stuff. I am not a firm believer in compression. I believe that it just needs to be tight enough to hold them without overdoing it. You don't want to squeeze them, and you don't want to pop the batteries, but you also don't want them to freely be able to expand out of their normal cell capacity. So there is 2 on this end to hold the sides of this battery in place, 1 here and 1 here, and you can see 2 in the middle and then 2 on this end. And what that allows you to do is to have 2 running down the center of the battery pack, and 2 on the back side and 2 on the front side of this battery pack, and make sure that you have all of the batteries firmly held in place. And that is exactly what I have done here, is make sure that everything is held firmly in place. Now, the back side of this cabinet is another piece of plywood here, and I painted these black so that the coloring would fade away, which has worked really well. It looks really nice in here, but it makes it very difficult to demonstrate. And then I attached this board to the side here for all the electrical stuff. When I originally built this, there wasn't really enough room, keeping in mind this is in an RV. And if I back up from what you're looking at here to show you where this is located, you can see here there isn't a whole lot of room in there for me to move around. So I had to basically make do with what I had. So I attached an additional support board here to hold all these battery components, knowing that these were really fixed in place. Now, that said, these batteries get ran in series, and then they get connected to the JK-BMS on the negative side, and then the positive side runs through a fuse, a off-on switch, and to the bus bars. And they both end up at a bus bar just like a regular battery would end up. Because theoretically, a battery is basically a series of cells ran together to create a battery bank, which is basically what they are. So in this case, you use 16 cells to create a 48-volt battery. You use 8 cells to create a 24-volt battery, and you use 4 cells to create a 12-volt battery, and you use 1 cell for all those little devices that you see, the little button batteries and all those type of things. Even the little stuff that you've got in your little remote controls and things like this has a little 3.6 volt lithium battery in it. So they're very, very common to have cells, but when you start combining them, you end up with different capacity. These are 304 amp hour battery cells. So when you combine them in series, the amp hour stays the same, but the voltage increases. So if you take 304 amp hours, it comes out to roughly about 15.6, 15.7, somewhere around 15 to 16 kilowatt hours at the 51.2 volts. Now, we use 51.2 volts because that is the standard voltage of the battery in its Goldilocks zone, not at the arms and the legs at the beginning and the end. And I'll show you a chart where the first 10% of a battery is where the voltage really spikes up, and the last 10% is where it really dips off. So you've got this this chart in the middle where the lithium iron, one of the very big benefits of a lithium iron phosphate battery is that it has this long range of very consistent voltage in the middle. And with the lithium iron phosphate as opposed to lithium iron, whereas if you have a cell phone, you have a lithium iron battery, the lithium iron phosphate, when they add that phosphate, it's a stabilizer. It increases the longevity of the battery, but it decreases the absorption rate, and it makes it not be able to be as charged, but it also lasts longer. So it has some perfect advantages to solar, where we're not charging at extreme rates like you would want to with a phone, but you're also charging much larger battery banks, and they're also a lot safer in the sense of they don't catch on fire, and usually they don't have runaway burnouts and things like that, where you would have a lithium battery would have. Okay.
I want to go a little bit more in detail about the JK BMS. This one is a particular catalog about a particular version, but the version on this particular page is really not what's important here. What is important is that we see the BMS here and notice that it has two big ribbon connectors that has up to, depending on the model of your BMS, in this case there's up to 24 different leads, meaning you can have up to 24 cells in your battery. Now, for a 48 volt battery, as we discussed before, you're only going to use 16 cells. So the leads that run off of 17, 18, 19, 20, 21, 22, 23, and 24, or however many you have, a lot of the BMSs only have 20 leads. Some of them only have 12 if you're working for a 24 volt battery. Some of them only have 8. And some of them, actually it's 8 cells for a 24 volt battery, or some of them only have 4 for a 12 volt battery. So if you were, depending on the inverter that you've got and the model number, it'll depend on how many of these leads that you have. But I wanted to point out that these leads are the ones that were connected in that wiring that we were looking at on the battery. And I don't want to take it apart to show it to you, but I do want to show you this diagram that basically outlines how the leads work, and I'll kind of show you what I'm talking about and how this works. So it's very important that you understand that these leads come away from this battery, and in this particular model there's 4 extra plugs with these leads, and the one that I just showed you there was only 2. So every BMS is different, and you need to be very careful to make sure that the first cell has the first wire and the second cell has the second wire, and so on and so forth. Here's how it starts off. The first lead connects to the negative post, and then every lead after that connects to the connecting bus bar or the negative post of the next battery. So you can see the second lead here comes up and goes around and connects to the negative post here. It also connects to the positive post here, allowing you to use lead 1 and 2 to measure battery 1. But the next every connector after that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, allows you to measure every cell's independent voltage. So if I take the lead from, this is 2, 3, and 4, if I take 4 and 5, then I can measure this cell 4's voltage. If I take 8 and 9, I can measure cell 8's voltage. If I take 15 and 16, I can measure cell 15's voltage. And if I take 16 and 17, I can measure cell 16's voltage. And then if I take 1 and 17, I can measure the entire pack's voltage. Keeping in mind that 17 being the last cell in the pack here is connected to the only one truly connected to a positive in the pack. So this allows the BMS to monitor whether you're a a 4 cell pack, an 8 cell pack for a 24-volt battery, or a 16 cell pack for a 48-volt battery. This allows the BMS to monitor every single cell in your battery pack and to specifically connect to each one of them for balancing. So in balancing case, if it determined that cell 2 was lower voltage, it would go find the higher voltage cell and it would extract some electricity out of it, store it, and then it would put it back into cell 2, causing this one to go down a tiny bit and this one to go up a little bit. That is what the active balancer means. It's actively taking power from the highest cell and transferring it to the lowest cell. And it does this one cell at a time. And that's why once your cells get over to, if depending on your configuration, 2.4 volts is the standard. Once your cell, 3.4 volts is the standard for auto balancing to start. Once they go over 3.4 volts, then it will start to auto balance and extract that power from the high cells and place it in the low cells. And thus the purpose for all the wires in the cell, it can go in and determine the voltage of the pack, it can determine the voltage of each cell, and it can transfer power from one cell to another. And this explains why it is so important that these cell leads are connected in the right spot so that it's looking for power between one cell being a maximum of 3.65 volts as opposed to 2 cells where the voltage would be too high, or 10 cells if you get them mixed up. And if you place these cords in backwards and get them in reverse order, you could have a real cell voltage problem. So if you're having any problem with these cells showing up the right power, or showing up too much power, or showing up in the wrong places, or showing up zero in the middle, make sure you check every single lead. It is a good practice on these lead wires to validate every one of them before you plug it in to the BMS and before you allow the wrong voltage to go to the BMS, because that can harm the BMS. So it's really important that you get every one of these correct, validate every one of them. Most people take the leads out of the leads off, and they get a labeling gun and they label every one of them. They put nice little connectors on the end, and then they attach all the leads, and then they take a meter and measure every one of them to make sure they're showing up with the right voltage in the right spot before they ever connect it to the BMS to be sure. All right, so let's look at the JKBMS application. And from here, you can see once you launch this application and you pick which battery you want to look at, if you had multiple batteries, then you can see here that we have an overview of the battery. It shows us the battery's total pack voltage. It shows us the different temperature gauges. It shows us the high cell, the low cell, and the state of charge, and the number of cycles that we've been through. This page can be very useful for taking a status review of the battery and understanding where everything is. So now let's move on up down to the cell voltages and kind of give you an idea of what they are. So you can see here in the bigger app, they're right in the middle of the configuration. We zoom in on the cell voltages, and here you can see the low voltage is highlighted with a yellow, or a red, I'm sorry, and the high voltage one is highlighted with the blue. Now, I've noticed that I've had the blue one on cell 16 has been quite a bit of an issue lately. So I'm going to show you here in a second how you can use this to help you identify things when you see things that show up consistently over a long period of time. Whereas you can see the red one moves around as it takes voltage and says it becomes a lower voltage cell isn't always the same, but the higher one seems to be staying the same, which could indicate a problem. So if we scroll down here now to the cell wire resistance, this shows you how good of a connection you have between each one of them. And as you can see, cell 15 and 16's cell resistance is a little bit higher than the other ones. So this tells me it might be time for me to go out and do a check on all of the connections within my battery and make sure that I've got them all torqued correctly, that I don't have any leads that are missing, I don't have any leads that are loose or wires that have come loose or been nudged or something with all of the testing and moving around that I've done the last few days. It's very possible that I've touched something. All right, moving on to the next area, in the next second tab across the bottom, you'll notice here you can configure the number of cells. This particular BMS handles between 4 and 20 cells. You also can configure the size of the amp hours of the cells that you put in. In my case, it was 304 amp hour cells. So you're going to want to configure it so that it knows how charged up things can be. On the balance trigger voltage, this means that the cell balance has to be out this far between the highest and the lowest cell for it to start balancing. And that is only part of the element. We'll get to the second piece here in a minute. And then calibration. Calibration voltage is suggested that you do the calibration of the voltage with a really good amp meter that you know is trusted, or you use multiple amp meters to make sure you get this right. And put those amp meters. I'll include a video on how to do the calibration, but briefly, you make sure the voltage is correct first, and then you do a draw or a charge on the battery and adjust the amperage to be accurate also. Once you do that, then the BMS calibration is complete, and the BMS can more accurately calculate the state of charge as it goes forward, because without the right voltage or without the right size of the battery or without the right amperage being detected as it's coming in and out of the battery, it won't be accurate and it'll be off more than normal. It's very difficult to get this right, and it is kind of an art, and you will have to do it more than once. You probably need to do a calibration, give it a few days to determine if it's off or on, or a couple of weeks in some cases, and you may do some minor changes after that in order to get it totally correct. All right. That kind of explains these first few settings here. Now, let's open up the advanced settings. And in the advanced settings, you are going to find this is where the meat of the configuration is. You start off with the starting balance of voltage. In other words, the cells have to reach 3.4 volts in order for the auto balancer to kick in. In addition to the configuration we did before, they have to be out of balance a certain amount before it happens. Then you have the max balance current, and that means that you're going to allow it to transfer at most 2 amps from one cell to another at a time. If you have smaller cells other than 304 amp hours, if you've got like 10 amp hour or 5 amp hour cells, you're not going to want to transfer that at 2 amps. You're going to want to lower that considerably to make it appropriate for the battery sizes you have. You have overvolt protection. Basically, this means stop the battery from overcharging your cells once they hit 3.65. Keep in mind, the BMS is looking at every cell in your battery, not the overall pack voltage of your battery with this configuration, meaning that it's going to protect each cell within your battery and prevent anything from harming it, hopefully. Now, as we go through the rest of these settings, you have the state of charge 100% voltage. When the cells reach 3.51 volts, my pack automatically resets to 100%. That allows me to reset any inaccuracies that I may have in my configuration or tuning. Overvolt protection restart, when it drops to 3.51, it'll come back on if it's been shut off at the high overvolt protection. Cell undervolt protection at 2.65, it'll turn back on if it was shut off because it was undervolt protection hit. And then if it gets down to 2.62 volts cell, it will automatically reset the pack to 0%, allowing you to bottom balance as opposed to top balance. Then we have the cell under voltage protection. When they hit 2.6, it goes into under voltage protection, and it'll power off at 2.5 volts per cell. This is intended to protect your battery from undercharging, overcharging, and discharging completely too far. I hope this helps, and now we can go into the overview. All right, so let's do a cost breakdown here. We had 16 battery cells at $1,112, a JK BMS, the B2A20S20P, which is basically a 2 amp balancer, 20 cells and 200 amps of power for $156. The Victron 275 amp on-off switch for $35. The T-Class fuse holder for $47. and a 250 amp T-class fuses. I did buy two, one for a backup and one for the real one, for a grand total of $1,417. All of the parts for these items are in the price list below, and the supplier for the battery cells is also in the price list below. The overall summary for the battery is, if you do it yourself, you can save approximately 2/3 the cost of your batteries. The problem is that it takes about 4 months to wait for the shipping to get in and for all of the batteries to be put together, assembled, and everything to be functioning. But if you have the time, it's well worth it, and it's well within our reach to build these batteries. Just be careful while you do it. Manageable, and it is a great savings in cost. Thanks for watching. We'll see you on the next video.